Good morning, everybody. Welcome to this course on principal stresses and strains. We'll quickly look at the overview of the topic at hand, and then we'll delve into more details. We're basically going to cover in definitions. In principle, as a fundamental definition, the principal planes are planes where shear stress is zero. So that means they don't have shear stress. And then they only have normal stresses. Normal as in 90 degrees to the plane, and they are called principal stresses. There are various methods, namely analytical and graphical, and we'll look at 4 different types of analytical methods where you have got a member subjected to a direct stress in one plane, and then a member subjected to like direct stresses in 2 mutually perpendicular directions, a member subjected to a simple shear stress, and then a member subjected to direct stresses in 2 mutually perpendicular directions accompanied by a simple shear stress. And then we have graphical methods where we look at Moore's circle, and under that we'll have 3 different approaches when a body is subjected to 2 mutually perpendicular principal tensile stresses of unequal intensities. When a body is subjected to 2 mutually perpendicular principal stresses of equal intensities but are unlike, that is, one is tensile and the second is compressive. When a body is subjected to 2 mutually perpendicular principal stresses accompanied by a simple shear stress. A bit of a tongue twister there, but let's quickly start with the analytical method, where we'll look at the first method where a member is subjected to a direct stress in one plane. Now moving into my whiteboard, let us consider a body which has a load acting on it. This load is a tensile pulling load. Let us consider a plane EF which is perpendicular to the line of action of the force. Right. Now, if we consider the thickness of this member to be unity, that is 1, then the area of section EF will be EF times 1. Simple, length into breadth, because if you look at the cross-sectional area, you will get a rectangle. That's the area that you will get. Now we can consider this as A. The stress in the section is given by our fundamental definition of stress will be force per area. In this situation, P by A. This is our fundamental definition. This is our equation 1. Now, if we look at the section EF, the stresses are normal stresses. There is no shear stress on this. There is no tangential stress on section EF. Now consider another section, FG, at an angle. Let me change the color of the pencil. Let us consider an angle FG at an angle theta. This is the plane FG at an angle theta. Now, area of this section will be similarly FG times 1. Again a rectangle, length into breadth. But we know from the trigonometric relationship in this triangle EFG that FG will be EF by cos theta times 1. Now going back, EF times 1 is nothing but A by cos theta. So that's the area of section FG. Now if you look at the stress on section FG, stress, which is sigma at G, will be again force per area, but in this case area of section FG. Now force, area of section FG will be A by cos theta. Solving further, we get P by A cos theta. P by A, again, getting from equation 1, P by A becomes sigma cos theta. This is your equation 2. Mind you, the ones that we are putting in the boxes, they can be considered as formulae that are useful for us in our numerical methods. So let's keep recording that. Now, a few points to note that this stress on section FG is parallel to the axis of the member. That is, this stress is along x-axis. The stress may be resolved in two components. One component will be normal to the section FG, whereas the second component will be along the section FG. So in a way, you will get one is a normal stress and another one is a tangential stress or a shear stress on section FG. Now let us look at how we can extract those. Let us consider Pn as the load on, or the component of the force P, which is normal to section FG. Now this will become P cos theta, taking from your engineering mechanics fundamentals. And again, let Pt be the tangential stress, sorry, tangential force along the surface of the section FG, and it becomes P sine theta. From our fundamentals of resolution of forces. Now let us consider sigma n as your normal stress. Now that is given by force per area. Force in this case Pn by area, in this case area of section FG is A by cos theta. Now simplifying this further, Pn is nothing but P cos theta by A by cos theta, which becomes P by A cos theta times cos theta, giving you P by A cos square theta, or P by A is nothing but sigma cos square theta. This is sigma n. This is your formula number 3. Now similarly, we can find out the tangential stress, sigma t, as the force, tangential force by area, which is A by cos theta. Now tangential force is P sine theta by A by cos theta, taking you to P by A sine theta cos theta. P by A again becomes sigma sine theta cos theta. Simplifying this further, I multiply and divide by 2, sigma by 2 times 2 sine theta cos theta. 2 sine theta cos theta becomes sine 2 theta from our trigonometric functions. This is your formula for tangential stress. Now, a few things to note here is that since these are dependent on theta, for the normal stress to be maximum, your theta needs to be 0, because cos 0 is 1. That is the maximum value that you can get out of cos square theta. So in a way, when your theta is 0, what are we trying to say? When the angle between FG and EF, let's look at the angle between FG and EF. If this angle becomes 0, then FG will overlap on EF. So in other words, we are trying to say that the maximum normal stress is nothing but the stress that is acting upon the plane EF, which is again sigma. So that is the maximum normal stress is when theta is equal to 0, or in other words, sigma cos square theta is equal to sigma, because cos square 0 is 1, and then you will have sigma, which is nothing but your stress acting on section EF. Now, another fact to note from your equation 4 is the maximum tangential stress, or the maximum value of shear stress acting on the plane, is when you have sine 2 theta as the maximum value. When will you have sine 2 theta maximum? Is only when 2 theta is 1, or 2 theta is 90 or 270, or in other words, when theta is either 45 or 135. That is when your tangential stress will be maximum. So maximum shear stress, this is sigma n and this is sigma t max, is equal to sigma by 2 sine 2 theta, where sine 2 theta is 1, which is either sine 90, or it becomes sigma by 2. This is just some understanding for us, and we'll look at a few problems in the next subsequent video, and then we'll go on further with the other methods. Stick around and hope to see you in the next video.